Hi everyone, thanks for tuning in. This is a STOC 2020 talk on online vector balancing and geometric discrepancy. My name is Makrand and this is joint work with Nikhil Bansal, Haotian Jiang and Sahil Singla. Let me start by introducing the vector balancing problem. You're given a bunch of vectors, t vectors in n dimensions. They all have infinity norm at most 1. And your goal is to give them plus minus signs, epsilon i's, so that every signed prefix is balanced. What do I mean by that? So if you look at any point in time and consider the vector summation epsilon tau v tau until some point, then the infinity norm of this vector is as small as you can make it. I will also call this vector, the signed prefix vector, the discrepancy vector throughout this talk. So this is a very well-known study problem in the offline setting, and here we're interested in the online version. And in the online setting, when a vector arrives, you have to immediately color it, and you cannot change this later. So in 1 dimensions, this problem is trivial, both online and offline. There is a simple greedy algorithm that gives you discrepancy at most 1. In 2 dimensions, I mean, even the offline problem gets non-trivial, but still it's possible to get discrepancy that is constant in this setting. I'm not going to tell you how this works, but this is a little bit non-trivial. But the crucial point is that in the offline setting, you have to look at all the vectors given to you. And this is not possible in the online setting. So what can you do? So you can always color randomly. This will give you discrepancy square root of t, because you will add t random signs. And it turns out that this is pretty much optimal because there is a matching lower bound in the adversarial setting. So if an adversary is giving these vectors, then you cannot do better than random coloring. And let me just show you the example because it's pretty simple. So let me call the discrepancy vector at some point to be dt minus 1. And the adversary gives you a vector vt, which is a unit vector, and is orthogonal to the current discrepancy vector. And the adversary always gives you orthogonal vectors. So in this case, just by Pythagorean identity, the L2 squared norm of your discrepancy vector, it increases by 1 at each step. And so the discrepancy at time t must be square root of t. So just because of this orthogonal example, you cannot do anything in the adversarial setting in the online model. But here, the main question that we want to answer is, can you do anything if these arrivals are stochastic? So if the vectors come IID from some distribution, can you match these offline bounds? And again, here, even in the stochastic setting, if you use random coloring, it will give you a square root t bound. And it does not exploit stochasticity. So what do we prove for this problem? We show that for any distribution over the minus 1, 1 and hypercube, the discrepancy in the online setting is at most n square log t with high probability. And we also show that this is tight up to both factors n and log t to some polynomials. So our results here, they match the best offline bounds up to, again, polynomial factors in n and log t. So for example, when n is 2, when you're in 2 dimensions, our results tells you that the discrepancy for any distribution in the online setting is at most log t. Much better than random coloring, which gives you square root of t. And let me also mention that previously Bansal and Spencer, which is a precursor to this work, they give an online bound of square root n log t when your coordinates of your distribution are also independent. But here we can handle any arbitrary distribution which can have crazy dependencies between coordinates. And as a caveat, let me mention that Bansal and Spencer, their setting is slightly different. They are getting rid of this log t factors, which you can only do if you consider discrepancy at a fixed time, or if you consider about expected discrepancy. But here we are interested in high probability bounds that are valid for all times, and then you cannot get rid of this log t factor, so these results are optimal. And the key tools, just as a keyword, let me mention what we use to prove this, is a nice trick that is called the decorrelation transform in the literature. And we also prove some anti-concentration bounds for uncorrelated random variables that we use to prove this discrepancy result. So this is the first problem that we consider. Let me define the second problem, which I will call interval balancing. Now you're given points on the unit interval, and you want to give them plus minus signs so that every interval is as balanced as you can make it. So minimize the difference between pluses and minuses in every interval. Let me also call this the discrepancy. So again, offline, this problem is trivial. Alternating signs gives you discrepancy at most 1. And in the online setting, if you are in the adversarial setting, if an adversary is giving these points, then it turns out that you cannot do anything non-trivial. So the discrepancy can be omega t in this case. This is a little bit non-trivial to see, so I'm not going to tell you why this is the case here. But if you are in the stochastic setting, so suppose these points are sampled uniformly from the unit interval, can you match these offline bounds up to some polylog t factors? So this is the main question that we want to answer, the second question. And let me mention that this problem was introduced by Jiang and Singla and has some applications to fair division and n-way minimization, which I'm not going to go into here. One can also generalize this problem and consider the well-known Tusnadi's problem in discrepancy. Now you're given a bunch of points in the unit square and you want to give them plus minus signs so that every axis parallel rectangle is balanced. So offline, also this problem is tricky and the best bounds are polylog t. And we want to ask if you can match these bounds in the stochastic setting, since in the adversarial setting, this is hopeless again. And one can consider this problem in d dimensions, which we do in this talk. So to solve these geometric discrepancy problems, we'll adapt the linear algebraic view and we'll reduce this by some discretization tricks that I will just tell you in a second to vector balancing. So how does this work? So let us divide our unit interval into half intervals recursively. So this gives us a tree, a binary tree of intervals. And let's say we stop when the bottom interval is of size 1 over t and the depth is log t. So why did we stop at log t depth? It's because each leaf interval gets exactly 1 point on average, since you only get t points. So if we ignore the smaller intervals, it's not going to screw up the discrepancy by too much. And I will call these intervals dyadic intervals, even the intervals that are not leaf intervals. And it suffices to bound the discrepancy of these dyadic intervals because every interval, you can decompose it as a union of log t plus 2 of these dyadic intervals. 1 for every level of the tree and maybe 2 leaf intervals to account for some error. For example, if you look at this interval, you can decompose it as a union of these 3 intervals. So to prove polylog t bounds, it suffices to bound the discrepancy of these dyadic intervals. And now the reduction to vector balancing is simple. So your coordinates will just be these dyadic intervals. They're 2t dyadic intervals. And coordinate is 1 if the point lands in the dyadic interval. So this is a 2t dimensional vector, but it turns out that it is sparse because when a point arrives, it can only land in 1 dyadic interval from each level of the tree. So only log t coordinates of this vector will be non-zero, and this vector is quite sparse. And the same thing implies that the coordinates are highly dependent. So when a point arrives, if it lands in the left side of this interval, then all the intervals in the right subtree will get a 0. So now we are interested in polylog t bounds for the geometric discrepancy problems. So now if you consider the vector balancing question, it has a huge dimension. The dimension of these vectors is 2t, but these vectors are sparse. There are only log t coordinates that are non-zero. So if you use random coloring, again, it will give you a square root t bound here up to polylog factors. And our previous results on vector balancing do not help here because they depend on the dimension, which is huge now. And now we want bounds in terms of sparsity, which we do not have previously. For these geometric discrepancy problems, we managed to get bounds in terms of sparsity. We proved that for the d-dimension 2 problem, for any product distribution over the 0, 1 cube, the discrepancy is polylog t with high probability, where the exponent in the polylog depends on the dimension. And we also show that this is tight up to polynomial factors. And again, these bounds match the best offline bounds we have up to polynomial factors. And as a corollary, if we plug d equals 1, we get the interval discrepancy is at most log cubed of t. So previously, Jiang, and Singla, when they introduced this problem, they gave a t to the little of 1 bound for interval discrepancy. So this beats random coloring, but this is quite far for polylog, and this does not generalize to Stochastic's problem even in 2 dimensions. And again, let me mention the key tool we use to prove this is the so-called Haar wavelets, which I will tell you about later. So let me state all our results in this setting in one place. So we prove a polylog t bounds for Stochastic's problem in any dimension, and we prove poly n log t bounds for vector balancing for any distribution. So for the rest of this talk, I will first briefly tell you what happens when you get independent plus minus 1 coordinates. So essentially the Bansal-Spencer setting. And in this case, I will show you a simple proof when you don't care about the log t factor. And then we will consider what happens when there are dependencies. And lastly, we'll consider the case of interval discrepancy via Haar wavelets. So let's move on to the case of independent coordinates. And again, let's start by revisiting random coloring. So why does it not work so well in this case? Okay, so let's even consider the case of 1 dimensions. So now you're given a bunch of plus minus 1 numbers, fixed numbers. And in this case, random coloring will give you square root of t even in 1 dimension. So now your signs, epsilon t's, they are uniform plus minus 1. So essentially, this is the analysis for Chernoff bound that I will remind you how it works, and in a way that will be useful for us later. So again, let us consider the exponential moment. So dt's are random variables, sum of t random signs, and lambda is some parameter. And instead of the exp of lambda dt, I will put cosh hyperbolic here, which is just e to the x plus e to the minus x over 2. So this gives you bounds on both positive and negative tails simultaneously, and it will be easier to work with for us. Okay, so let me do an online analysis for this case, essentially. So the vector dt is the sum of dt minus 1 plus epsilon t vt, where epsilon t is the sign you choose at the tth step, and vt is the fixed number. I've written in this way because I want to do a Taylor expansion as is usual in Chernoff bounds. And the first and second derivatives of cosh hyperbolic are sine hyperbolic and cosh hyperbolic respectively, where sine hyperbolic is e to the x minus e to the minus x over 2. So now just by Taylor expansion, the change in the potential from time t minus 1 to t is approximately the linear term of the Taylor expansion plus the quadratic term. So now the update is lambda epsilon t vt. So the linear term, that's what you get. And in the quadratic terms, these things are squared. So now note that epsilon t is a random sign, uniformly chosen, independent of everything. So the linear term here becomes 0. And the quadratic term, the epsilon t vt term, just goes away because it's plus minus 1 always. So what you get is that the change in the potential is lambda squared times the previous potential value. So what this implies is that potential increases multiplicatively by 1 plus lambda square at each step, and at time t, it's roughly e to the lambda square t. So now if you want this potential or this exponential moment to remain bounded, you need to set lambda to be very tiny, 1 over square root of t, and then you get a bound of 1 over lambda or square root of t on the discrepancy. So the reason random coloring was so bad is because the potential increased very fast multiplicatively. And to manage this growth, we needed to set lambda to be very small, square root of t inverse. And the reason why potential increased so fast is because the quadratic term was always positive and increased the potential. and we were being stupid and we chose the sign epsilon t at random. So the linear term did not help us at all. So now we didn't have to do this. So for example, we could have chosen the sign epsilon t cleverly so that the linear term is negative and it offsets the increase due to the quadratic. And we can also play around with this lambda. And since lambda is less than 1, lambda square is much less than lambda. So we can help lambda to balance these two terms out. And this is the main idea to prove discrepancy of square root n log t for independent plus minus 1 coordinates. So the algorithm is again very simple. We just use the greedy algorithm with respect to the same potential that we used in the Chernow bound analysis. So cost hyperbolic of lambda times the discrepancy in coordinate I. This is essentially the soft max of the discrepancy in each coordinate, and lambda is some parameter. And the analysis of this algorithm will just reduce to using anti-concentration of independent plus minus 1 signs, essentially Khinchin's inequality, to argue that the linear term is typically negative and cancels the increase to the quadratic term. So in particular, if we can say that this potential is bounded by Pauli and t at any time, then the discrepancy is bounded by 1 over lambda times log n t. And now we want to set a very large value of lambda, n to the minus 1/2 in this case, that will imply our claim. So note that for random coloring, this was t to the minus 1/2, and now here is much larger. Okay, and let me just mention like a very simple scenario just to convince you that you can set lambda to be n to the minus 1/2 here. So suppose the change in your potential, the linear and quadratic term look like this. Okay, so this is just the example, and this can happen also. So the linear term is minus lambda times some a, where a is some number, and summation xi, absolute value. Okay, so this is always negative if summation xi is non-zero, and the quadratic term is this summation xi squared with a lambda square there, where x1 through xn is your incoming vector, which is all plus minus 1 independent. So now the second term here is always n, because xi is at plus minus 1, and the first term can be 0, in which case it does not help us. But since the xi's are uniformly at random, plus minus 1, this is typically square root of n because of anti-concentration. So then you can set lambda to be roughly 1 over square root of n, and so that these two terms balance out, and delta phi is negative. Okay. So I hope this gives you an idea why you can set lambda to be so large and get our claim. So this was the case of independent coordinates. When you have dependencies, then you might not have any anti-concentration, because, for example, your summation xi could always be 0. So to handle this, we will need additional idea, and let me give you an example to illustrate it. So suppose you are in 2 dimensions and your distribution is, let's say, over plus minus 1 vectors in 2 dimensions as follows. So with 1 minus delta probability is uniform over 2 vectors, where the coordinates are always the same, and with some delta probability is uniform over the other 2 vectors. And suppose your discrepancy vector at some time t looks like m and minus m. So the absolute value is the same, and the discrepancy is the same, but the signs are different. So now if we get one of these 2 vectors which have opposing signs, then you're in good shape, because you can choose a sign appropriately and decrease the discrepancy in both coordinates. But if you get one of these vectors, then you are in bad shape, because no matter what sign you assign them, one of the coordinates, the discrepancy will always increase. So now let's consider these 3 regimes. So when delta is large, so this is the case for uniform distribution over plus minus 1. So in this case, delta is 1/2, then you're fine, because reasonably often you get one of these 2 good vectors, and then you manage to decrease the discrepancy. So now what happens if you never get any good vectors when delta is 0? Then in this case, you can notice that the discrepancy vector remains always in the span of this 1, 1 vector. So this is essentially a 1-dimensional problem. And in 1 dimension, even online, this problem is trivial. But this is not very obvious to you until you change the basis and make sure your x-axis is aligned with this 1, 1 vector. So for delta small, essentially that's going to be the new idea, is that instead of working in the coordinate basis, you change the basis and choose a more appropriate basis to work with. So essentially, to prove our theorem that for any distribution, the discrepancy is at most n squared log t, we will change the basis, and the right basis is one where the random variables are uncorrelated, by which I mean that the expectation of xi xj is 0 for every I different from j. So note that this is a condition only on the expected value and not even pairwise independence. And the analysis of this algorithm will reduce to using the anti-concentration of uncorrelated random variables to argue that the change in the potential is small. And again, for uncorrelated random variables, anti-concentration does not seem to be studied before. And we show that in this case, you get a very reasonable lambda here, which is 1 over s times L if the incoming vector is s sparse and all the coordinates are bounded by L. Okay, so if you can find the right basis to work with where the random variables are uncorrelated, then essentially you get our result. So what's the right basis to work with? So here, nice trick called the decorrelation transform from the literature is very useful. So suppose you have a mean zero vector which has a covariance matrix sigma, whose eigenvectors are given by this matrix U, and lambda is a diagonal matrix of the eigenvalues. Then y equals U transpose X. This is an uncorrelated random vector. So the covariance matrix of these vectors of these vector y will just be a diagonal matrix lambda. Okay. So essentially, this means that these random variables, if you change the basis to eigenbasis of the covariance matrix, they become uncorrelated, and then we can apply our anti-concentration results. So this gives us the claim for any arbitrary distribution, but we do not get bounds in terms of sparsity in general, because when you move to a new basis, you lose a square root n in the discrepancy. And when you move to a new basis, you may also lose all sparsity. So we cannot use our anti-concentration, which only depends on the sparsity in the new basis. So to handle this, we will need a Haar basis. For this, again, let me remind you of the reduction to vector balancing first. So again, it suffices to bound the discrepancy of these dyadic intervals, and the coordinates of our vectors for dyadic intervals. So this vector was log t sparse, and we want polylog t bounds now. Again, if you consider the potential in the original basis, which is just cosh hyperbolic of lambda times the discrepancy of the dyadic interval, turns out that this does not give you subpolynomial bound. There are some bottleneck examples for this. But if you change your basis and move to the so-called Haar basis, so Haar wavelets are functions over the unit interval that look like this. So again, each Haar function is supported on a dyadic interval, but on the left half of the dyadic interval they're +1, on the right half they're -1, and outside the dyadic interval they're 0. And the crucial property of these Haar wavelets is that they form an orthogonal basis for L2 integrable functions on the unit interval. Now, if we use cos hyperbolic potential in this Haar basis, by which I mean if you look at the vectors where instead of the indicator functions of the point landing in the dyadic interval, you just use these Haar functions, then again you get a 2D dimensional vectors, which is now again sparse in this Haar basis. And the orthogonality of this Haar wavelets, it implies that the coordinates are uncorrelated, and now they are sparse in this new basis, the Haar basis, so we can use our anti-concentration for uncorrelated random variables. And it turns out that you also don't lose the square root n when you transform the discrepancy back to the original basis. And it also easily generalizes to Snardy's problem by taking tensor products of these one-dimensional Haar bases. That's pretty much the end of the talk. So let me leave you with some open questions. We consider the case of IID arrivals. So what happens when each vector is drawn from a different distribution? So this is a little bit tricky because this also captures the offline problem, but now you want an online algorithm for this. And a strictly harder question is, what happens if you have an oblivious adversary. So for non-adaptive adversary, you can still hope to get a polylog T bounce, let's say in 2 dimensions. And for adaptive adversary, we know that you cannot beat random coloring at all, but for oblivious, it might still be possible. And this is a very interesting question. So that's it. Thank you very much.